MPLS architecture. Introduction to MPLS. MPLS means multi-protocol label switching is a scalable protocol independent forwarding mechanism used in high-performance networks. It improves packet forwarding speed by using short, fixed-length labels instead of complex IP lookups. Originally developed to enhance ATM networks, MLS now supports various transport technologies like Ethernet and IP. MPLS operates between Layer 2 data link and Layer 3 network, often called a Layer 2.5 protocol, widely adopted by service providers for traffic engineering, VPNs, and QoS in enterprise and telecom networks. Why MPLS? Motivation and benefits. Traditional IP routing relies on longest prefix matching, which can be slow and inefficient for large-scale networks. MPLS enables faster forwarding through label-based switching, reducing processing overhead at each hop. It supports traffic engineering by allowing explicit path control, improving bandwidth utilization and network reliability. MPLS simplifies network design by decoupling forwarding decisions from complex routing protocols. Enables advanced services like Layer 3 VPNs, QoS prioritization, and fast reroute for fault tolerance. Core components of MPLS. Label switching router LSR, a router that forwards packets based on MPLS labels, including ingress, egress, and transit LSRs. Label edge router LER, located at the edge of an MPLS network, adds, pushes, or removes pops labels on incoming outgoing packets. Forwarding equivalence class FEC, a group of IP packets treated the same way for forwarding, such as those with the same destination. Label switched path LSP, a predetermined path through the MPLS network that packets follow based on labels. Label distribution protocol LDP, used to distribute labels between LSRs to establish LSPs dynamically. MPLS label structure. An MPLS label is a 32-bit field inserted between Layer 2 and Layer 3 headers in a packet. The label contains a 20-bit label value, a 3-bit traffic-less field for QoS, a 1-bit bottom of stack flag, and an 8-bit TTL field. The bottom of stack bit indicates whether this is the last label in a stack, used in hierarchical MPLS setups. Multiple labels can be stacked to support services like MPLS, VPNs, and traffic engineering tunnels. Labels have local significance, meaning each LSR can assign its own label value for the same FEC. Label switching process. When a packet enters an MPLS network, the ingress LER classifies it into a FEC and enables a label. The labeled packet is forwarded to the next LSR, which swaps the incoming label with a new outgoing label. Each transit LSR uses a label forwarding information base LFIB to determine the outgoing interface and label. At the egress LER, the label is removed and the packet is forwarded using standard IP routing. This process avoids deep IP lockups and every hoop, significantly speeding up forwarding. Label Distribution Protocol LDP. LDP is the most common protocol for automatically distributing labels between LSRs in an MPLS network. It establishes LSPs by exchanging label mappings with neighboring LSRs using TCP and UDP. LDP binds labels to FES based on the underlying IGP like OSPF or ISIS routing table. Each LSR advertises its label for a FEC to its beats between a inconstructed forwarding database. LDP ensures that all LSRs agree on label assignments, enabling seamless and end-to-end LSPs. Traffic engineering with MPLS. MPLS enables explicit routing through Resource Reservation Protocol, Traffic Engineering (RSVP). RSVP allows network operators to set up constrained LSPs that follow specific paths, avoiding congestion. It supports bandwidth reservation, ensuring critical applications receive guaranteed network resources. MPLS-DE can reroute traffic around failed links using pre-established backup paths fast reroute. This improves network efficiency and reliability, especially in large ISP and in enterprise backbones. MPLS and quality of service QoS. The three-way traffic class field in the MPLS label supports QoS by carrying priority and drop precedence information. LSRs can only apply different forwarding treatments based on the traffic class value, such as expeditious or assured forwarding. QoS policies can be applied at ingress LERs to classify traffic and assign appropriate labels. This enables services differentiable for voice, video, and data traffic within the same network. MPLS QoS integrates well with different models, providing scalable traffic prioritization. Next, MPLS Virtual Private Networks (VPNs). MPLS supports Layer 3 VPNs using BGP to distribute customer routing information across the provider network. Each customer site connects to a provider edge PE router, which maintains separate virtual routing tables VRFs. Labels are used to isolate customer traffic and ensure privacy without encryption. A two-label stack is used: outer label for transport across the core, inner label for customer-specific routing. This allows multiple enterprises to share the same infrastructure securely and efficiently. MPLS in Service Provider Network. MPLS is the backbone technology for most modern ISPs due to its scalability and service flexibility. It ensures providers to offer differentiated services like L3 VPN, L2 VPN, and Ethernet services over a unified infrastructure. MPLS simplifies network operations by reducing dependency on multiple overlap protocols. It supports seamless integration with existing IP and optical networks. Major providers use MPLS for inner data center connectivity and cloud access services. MPLS also traditional IP routing. Traditional IP routing uses hop-by-hop destination-based forwarding with variable lockup times. MPLS uses pre-established paths, LSPs, and label swapping, resulting in faster and more predictable forwarding. IP routing lacks built-in traffic engineering. BPLS, MPLS enables explicit path control and bandwidth management. MPLS supports advanced services like VPNs and QoS more efficiently than pure IP networks. However, MPLS adds complexity in configuration and management compared to standard IP routing. Challenges and limitations of MPLS. MPLS requires careful planning and configuration, especially for LSPs and label distribution. Interoperability between vendors can be challenging due to protocol implementation differences. Scaling large MPLS networks demand robust control plane protocols like LDP and RSVP. MPLS does not provide encryption, security relays on network isolation and access control. With the rise of SDN9 segment routing, some networks are exploring alternatives to traditional MPLS. Real-world application and case studies. AAT uses MPLS to deliver it AAP service and internal customers.